Okay, so P12.7 seismic waves. What we've got is we've got two types of seismic wave. You've got the first type of seismic wave is known as a pressure wave or a P wave, and the second type is known as S wave or a stress wave. Okay, so that's pressure and that's stress. And the reason why I mention this, and I'll use different colours for these two because they make it a lot easier. So let's go for red for S for stress, and let's go for green for a pressure wave. Okay, so P wave, pressure wave, stress wave. So if you imagine two rocks pushing together when they have an earthquake, you get a pressure wave. So if they're pushing together, it's going to give you a clue as to what type of wave it is. Pushing together, side to side movement. That is your transverse wave. No, wrong one. Sorry. Longitudinal. And your stress wave is when they start moving beside each other like that. So this one, and they're going up and down. So this one is your transverse wave. Now, the key thing you need to know about these are what they can travel through. And this one can't travel through liquids. Just won't do it. Okay, and that's the difference between the two when it comes to earthquakes. That's the useful fact. Transverse wave can't move through a liquid, and the reason for that is if you imagine that you've got a liquid, none of the particles are joined together. So if this one starts moving up and down, this one here looks at its neighbour and says, "What on earth are you doing? I don't need to move up and down." Whereas for a P wave, if this one comes in here and it shoves its neighbour that way, well then that one is going to move that way. Okay, so P wave, it doesn't matter if it's connected or not, because it's going to shove into it and push it that way. This one is moving up and down, and this one goes, "What are you doing?" Okay, so S waves can't travel through a liquid, P waves can. Let's take that into account when it comes to the next bit. Okay, so if this is our Earth, and we have an earthquake in the Earth, somewhere there, for example, what you'll see is this. You'll see, and so waves will go out in all directions, and both S waves and P waves will go out in all directions. Okay, and they get recorded here at your earthquake center. Okay, directly above it, that would be the shortest route. That's the one that's going to receive it first. That is known as the epicenter. Okay, the epicenter of the earthquake. Now, what's going to happen next is this. These two waves, the epicenter receives a signal, and it doesn't just receive the signal from the first wave, it receives what's called an aftershock. What's an aftershock? Well, this is the crust, and this is the mantle, and this is the outer crust, and this is the inner crust. Sorry, outer crust, inner crust, inner core, and outer core. Okay, so but how do we know all of that? The deepest hole we've ever dug is about 50 kilometers. And it's about that. Okay, that's the deepest hole we've ever dug. So how do we know about all this that's going on inside? Well, we know about it because of the earthquake, and because of what we know about P waves and S waves, which are pressure waves, stress waves, longitudinal waves, transverse waves. So, what did I mean by aftershock? So you get your shock, then you get your aftershock. What's the aftershock? Well, it goes off in all directions. When it gets to a boundary, some of the wave is transmitted, some of the wave is reflected. which means that what you've got there is this one here is taking a much quicker route, so that one's going to get there first, and then this one takes this amount of time here. And that's how you know how deep down the earthquake happened. It's the difference between the two. Okay, so the deeper it is, the less time there is between the shock and the aftershock. The higher up it is, the less time there is between the shock and the aftershock. The more time there is between the shock and the aftershock, sorry. So that's how we know how deep down it is. We know that the mantle must behave like a liquid because we get both P waves and S waves. And people get confused by that because they think of magma as being a liquid. But it is a liquid, but it's so compressed and it's just molten rock that it acts like a solid, a bit like custard. Okay, non-Newtonian fluid. It acts like a solid. Okay, what we've got next is we've got the outer core. And what happens with the outer core is this. Only you get another reflection a little bit later, but this time the only one that comes back is the P wave, and that tells you that the outer core must be a liquid, and in fact we know it's liquid iron, and it's reflected, which means that, you know, and nickel, sorry, iron plus nickel. And it's reflected, which tells you that there's another change in density here, which means there must be an inner core. Okay? So, what you know so far, so what the signal that you're going to receive so far is going to look like this. That's your shock. That's the earthquake. You're then going to have to wait a little bit of time. That's your aftershock, okay, and that's the reflection from the mantle. Then you're going to have to wait a little bit of time, and then that is going to be, and so far with your shock you've got green and red, you've got P waves and S waves. Aftershock you've got green waves and S waves, but for the next one, just S waves. So this is what you're going to receive. So you can receive P rays and S waves, P rays and S waves a little bit long time later. So, and we know that how long it takes. So this time there, so that time there, that's going to be how long it took for it to go from there and back. Okay. So that's going to be how, and you can use that to work out how thick the inner core is, and then again you can do it again. And you can work out how thick, so that's going to be how thick the mantle is, sorry, and this one is going to be how thick the inner core, the outer core is. Okay, now what you get now is you get something else happening. Okay, so in this bit here, you're going to get your, when it goes into something that's more dense, its direction changes because it gets refracted by the core, okay? So it goes in here, goes into something that's more dense. If it's more dense, then the angle's going to get less, so it changes direction slightly. And you end up with it getting refracted. And you get two types of shadow. Okay, so these two bits here, they're known as P wave shadows, and because not even the P waves are there and there because of the refraction effect of the solid core, but also the whole area is a complete S wave shadow. And that's because the outer core, sorry, is given a complete shadow. So you're only getting, so from this region, so that region there is the only bit that receives S waves, whereas in this area here it doesn't receive any S waves at all because they can't get through this liquid iron and nickel outer core, so they're completely absorbed by that. And you still get P wave shadow, but they're quite small, and they're due to the refraction of the P waves by the solid iron core in the middle, and that's how we know that the iron core in the middle is solid. If it wasn't solid, there wouldn't be a change in density, you wouldn't get this second signal here. Okay, and then if you use the time and then you use the speed equals 2 times the distance, that you can work out how thick the different layers of the earth are.